Ah, great. Thanks a lot.
Good choice.
Yeah.
Salman will introduce you.
Is there is a natural break in the thing because I'm doing networks, noisy networks, and then data compression.
Okay. Yes.
So of course I don't know how the balance will work out.
Okay.
So is it worth? Is it better to break at the natural break or break at the whatever you suggest? What do you? Because I don't know how long. The problem is I don't know the timing. So
you don't know the timing. Okay.
How it work?
It's whatever. I mean, you can kind of read the audience and tell if they need a break. I can say overall the week is like the only source coding is like whatever you cover in the second half. So.
Oh, I see.
And some students commented at breakfast this morning that it was a very kind of wireless heavy, which is true.
So so then I will have to then that might.
So they might appreciate more emphasis on that.
Okay.
That's much clearer, but it's a little bit.
That's fine.
Like a movie theater.
Yeah, that's fine.
So which one do you prefer?
That's fine. If whatever is better for them to see is if this is better, then I think.
Before I
Sure.
David, keep coming.
Okay, good morning everyone. Here we are, last lecture, and a very special lecture. So our speaker today is a professor from UCLA. He graduated in 1998 from Stanford under Tom Overstreet, and then he joined a year at AT&T Shanghai, and after that spent about 7 years at EPFL. And now he is a full professor at UCLA. He has made many contributions to wireless communications, multi-user information theory, has received many awards, honors, including the Donald King Prize for the best tutorial paper, and also the Power Foundation Award for contributions to wireless communications. So join me and welcome Professor Suhas.
Thanks, Salman, for the kind introduction. And thank you, both Salman and Aaron, for organizing this very nice workshop and inviting me. I've enjoyed it so far. So I know this is the last day. So most likely you'll be very tired. I hope I don't tire you more. So what I would like is I have material for the whole time, but I would prefer that this is as interactive as possible. If you have questions and so on. So the way we will do this is that we have the split screen. I can write on this. So, but I'll put this in full screen mode when I'm talking, and whenever I need to write something, or if there's a question and I can write, I will switch to the other and I can do that. So that basically is how we'll try to organize this. So this talk has essentially two parts, one more on wireless and the other more on data compression. And this work has been done over the last few years with several collaborators. Salman, the first part of the talk has a lot of collaboration with Salman. Jun Chen and Shlomo and Chao Tian, we did a lot of the source coding and data compression stuff. David Shea, Sohail Mohajer actually also was involved in the source coding as well as some of the wireless stuff. Ifer was with wireless. Christina Fraguli also with the wireless part, some of the wireless parts. So there are many other people who I've interacted with and learned a lot from. So not all of them are on this slide. Okay. So just a very broad introduction. So what is the goal? The goal is that you probably have heard a lot about communication over networks, and we all know that there is a lot of unresolved questions. And what we've been trying to do is, in almost all cases, like in noisy networks, in lossy data compression, source channel coding, there is really no what is called a characterization. So Shannon, when he developed information theory, set a very high standard in terms of what it means to solve a problem. what he did was essentially showed the solution for a fairly simple model, a memoryless channel, but showed what is called a single letter characterization, which means that you can write down what the rate achievable is as a finite dimensional optimization problem. Now, it's surprising because the schemes that were allowed to actually achieve these rates were using large block lengths, and in principle essentially could become an infinite dimensional optimization problem. And it was amazing that such a problem, the characterization of rate for such a problem actually reduced to a finite dimensional problem. Now, in networks, this kind of a reduction has been much rarer. There are very few problems which have admitted such complete characterizations. And so most of the problems that have been studied in networks have actually been open, and open in the sense that there is no, it's not open in the sense that there is no way to even tackle the problem. There are schemes clever schemes that have been developed to actually develop codes for such problems. There are good outer bounds to develop for such problems. But the fact that there is no characterization, which is a single letter characterization, a finite dimensional optimization problem, that's what we mean by unresolved. Okay? So the philosophy that we are going to take is in a sense a way to think about it as a MSB in some ways, to say that what are we really fighting for? How much are we, if we have schemes that have been proposed, is the gap from what could possibly be done very large, or is there a bounded gap? So our philosophy is really to try to see, at least for a class of problems, whether there are approximate solutions. And the kind of approximation that we're going to seek is the following. So it is going to be an additive approximation, in the sense that we want the approximation to depend only on essentially the problem structure, not on the particular channel parameter or problem parameters. Like we'll see that when we go along. But when we talk about noisy networks, it should not depend upon things like channel gains, SNRs. When we talk about data compression, it should not depend upon distortions, etc. So that's really what we mean by universal approximation. And basically, of course, from an engineering point of view, essentially the hope is that these kind of approximations already give us enough insight and say how much we're really fighting for, and maybe be able to get enough insight for engineering practice, and maybe it's essentially enough in that sense. Because if you really think about engineering, we have already approximated the problem. We have created a model for actual reality. Now, if the model itself has certain amount of inaccuracies, to essentially solve it exactly for that model may not necessarily mean that much to engineering practice. There may still be a further approximation. So what we are saying essentially is that maybe as a first step to understanding how much we are really losing in terms of our understanding, is there a lot to be gained, or is there an approximate characterization? And that's really what this talk is about. So as I said, there are going to be two parts to this talk. Essentially, the philosophy is to develop models which are simpler, solve them, use the insights to get the approximations. The two parts, the first is on wireless networks, and the second is on data compression and also source channel separation. All right, so we'll start with the wireless part. So essentially, I think you have heard a lot of talks about wireless, so this can be fairly quick. But just to recap, the two essential characteristics of wireless is broadcast. So when I'm talking, everybody gets to listen, but they may get to hear a different version. And there is superposition, which means that, say, two people are talking. What I get to hear is the mixture, not the individual components. And that's really the distinction of wireless. And in a sense, while network information theory has had a lot of insight into how to use these properties, in current wireless systems, This is really, in a sense, ignored, in the sense that almost all systems really work on creating point-to-point links. And there are good reasons, in the sense that in terms of complexity of design, in terms of being able to actually scale it to a large number of users, etc., they really, the systems are really creating point-to-point links. So cellular systems really create point-to-point links through CDMA or OFDMA access. Opportunistic scheduling is something that is done where you schedule the best user, but it's still a point-to-point channel. So the reason for that, and in some ways the advantage of getting to point-to-point channels is that in the last 10 years or so, or 15 actually, there's been a very good understanding of how to do point-to-point communication. So, for example, if you take space-time codes or MIMO, Turbo, and LUPC codes, effectively the point-to-point links are being operated very, very efficiently. So if somehow you can just think of creating point-to-point links, then essentially that means that the problem is tractable from an implementation point of view. But essentially the engineering question is this a good approach? So what are the current trends that you see in wireless systems practice? In a sense, one challenge is that there is tremendous amount of traffic scaling. So if you look at any, almost all of you have smartphones, and you really essentially are looking at downloading video and all sorts of applications that really create a lot of traffic. So essentially there's a doubling of wireless data traffic almost every year. Another thing that is happening in wireless systems is that it's very heterogeneous. So you have managed networks like cellular networks, and there are unmanaged networks, chaotic deployments of wireless Wi-Fis, which you see all over the place. So it's very chaotic. And then essentially a huge number of phones and a huge number of devices, increasing the amount of density of devices. So essentially, the way wireless systems are currently approaching this problem is that you put in more hotspots, put in more base stations, etc. So essentially the network density increases. That's the one way to improve. So if you're already operating the point-to-point link at a very efficiently, the only way you can essentially improve the rate, if you still want to stick to point-to-point, is essentially improve the signal-to-noise ratio. And that way you try to bring the access point and the clients close by. And that's really what this dense deployment does. You also have very aggressive frequency reuse, which means that in older systems, in 2G wireless, etc., the way it worked is that if you used a certain frequency band in a cell, the next time you used it was like 6 cells apart, or it was a very large amount of generous frequency reuse. That's very inefficient use of spectrum. So there's very aggressive frequency reuse, which means that almost all the adjacent cells are using the same frequency almost. So that essentially means that there is the superposition part of wireless actually comes into play a lot, and they have to deal with it. And the third thing that people are trying to do is to try to deploy relays, not just to improve coverage holes and so on, but to improve throughput. And that's something that we will investigate. In all these, essentially, the missing component, as I said, is ultimately you're limited by the wireless properties, the fact that there is signal interference, and we need to devise schemes that exploit these properties rather than create point-to-point links. And this is sort of what we will try to address in this talk. Okay, so I want to make a distinction in what interference means. So think of a single base station trying to communicate with a mobile unit. So as I said, the wireless channel is broadcast. So if whatever the base station is saying, if there is a helper node, say a relay node available, it gets to hear what the base station is transmitting. So does the mobile unit. So this is broadcast, and the relay can try to help. And when it transmits along with the base station, what it transmits gets superposed along with what is sent by the base station at the mobile unit. So this is superposition. So one way to think about it is that it is, there is signal interference. Yes, there is signal interference, but there is only a single flow. That is, this relay does not have a message of its own. It is only trying to help what the base station is sending. So we want to say that there is only, in a sense, signal interference. And the contrast is the following. Suppose there are multiple flows. So they say there are two base stations that are trying to communicate with their own mobile unit. So there are, say, two adjacent base stations. And one is trying to communicate to one of its mobile units, and the other one is communicating to the other. And there's very aggressive frequency reuse, which means that they're both transmitting at the same frequency. Which means that the transmission of base station 1 could actually interfere with the transmission of base station 2 to mobile 2, and vice versa. Now, the distinction between the first case and the second case is the following. Mobile 1 is only interested in what base station 1 has to say. What the message sent by base station 2 to mobile 2 is not useful. So in this case, I want to make the distinction that at the physical level, there is superposition or interference in the signal, but more importantly, at the message level, there is interference. That is, it is getting something which is related to a message that it is not interested in. So I want to make this distinction between a single flow and multiple flows. In single flows, even though there is physical interference, it's only signal interference. There's no, in a sense, message interference. All the signals, in some sense, are useful. In message interference, on the other hand, it could be that some of the messages, some of the signals, so to speak, are not useful. That's really the distinction. In both cases, the problems have been unresolved for many, many years. And in this case, in this talk, what we will talk about is for cases for Gaussian networks, for which we demonstrate that when there is only signal interference, that is, when there's a single flow, the problem is much easier. Even though there is superposition and so on, we can approximately characterize the capacity for arbitrary networks. But as soon as you go to multiple flows, the problem becomes very delicate. You can do this even for simple networks. You really have to specialize to the schemes for those networks. So there's a stark difference between these two cases. So let's start with single flow networks. So the model that we'll work with in this case is the Gaussian model that you might be very familiar with. That is, the signal received at any node is essentially a superposition of all the transmitted signals. That's basically the superposition property of wireless. And any node I which sends is heard by every node in the network, transformed by Hij, which essentially is the broadcast part. So it's essentially capturing both the broadcast and superposition superposition properties of wireless. And essentially the channel gains essentially really capture the signal strengths. Okay? So the first thing we will do is to understand this by simplifying the model. And we will develop a deterministic channel model that will help us understand this. And the deterministic channel model essentially philosophically tries to think about focusing on the signal interaction rather than the noise. And with the deterministic model, we will be able to get insights to get approximate characterizations. And this will work both for the single flow and multiple flow networks. Okay. So deterministic, in a sense, the deterministic models and approach actually has a very long history. In fact, when multi-terminal information theory was really started in the 1970s, people actually did think about deterministic channels. In fact, the broadcast channel, which is an open problem for 40 years or so, for the deterministic case is actually completely resolved. It was resolved in the 1970s itself. The deterministic relay channel, which is a 3-node network, was also completely resolved in the 1970s. Deterministic broadcast-only networks, and arbitrary networks, was actually resolved in the 1970s as well. In fact, if you think about this case, it's really a precursor of network coding. It really is captured a lot of the things that network coding discovered. And in fact, what we said was the two-flow problem, the interference channel, the deterministic version actually, with a special structure, was also completely resolved. So in some ways, in the 70s itself, people did actually realize that deterministic channels and approaches are actually very successful. And the insights, the only thing that they perhaps did not do more is with using these insights for more general networks and developing a more systematic way of thinking about it. Then about in the 1990s or so, and the late 90s, this sort of approach actually was revitalized in terms of thinking about network coding. And network coding, which essentially studies flows on graphs, was demonstrated something that was very surprising to many people at that time, which is that if you take a graph and you want to send multiple information flows, but all the destinations are interested in all the information sent, then you can actually achieve the min cut for all the destinations simultaneously if all the min cuts are equal. And that's basically was also shown by mixing information over the relay networks. In some ways, as I said, the result of RF was actually very closely related. And when we go through our proof, we'll actually recover a special case of the network coding. So I'll say more about it when we get there. And essentially what we have been thinking about is deterministic approximations. So let's start with the models itself. So the deterministic model is essentially saying, the linear deterministic model says that you want to, the received signal is a linear combination of the transmitted signals, but over a finite field. And in the examples, this combination is really a shift matrix. We will see that in a minute. And we also deal with what are called general deterministic networks, where there is no noise, but there's a general deterministic function which captures the interaction. So here is an example. So the idea is that if you have a source that's transmitting a signal, we can think of representing this in terms of if you think about a binary expansion of the real signal. And depending on the channel strengths, the number of bits exposed to each of the receivers depends upon how strong the channel is. So for example, if you think about this as being above the noise floor, it really says that how many bits or how much of the signal that you see is above the noise floor. So in this particular case, for example, you can say that here the channel strength is such that 5 bits are above the noise floor, 2 bits are above the noise floor, etc. So that's the broadcast part. The superposition part of it is saying that when 2 signals are transmitted simultaneously, again you scale it by how many MSBs are exposed due to the channel strength. And then when they mix, we essentially do modular addition. Now, modular addition seems arbitrary at this point, and there is some intuition as to why one would try to do modular addition, which is essentially saying that when you do real addition, there is no carryover. But another way to really think about this is to really think about this model as getting insight into what we do for the real and Gaussian real channels. So the way I would use this model right now for the next few slides is really as a model which is inspired by this approximation, but really enables us to develop insights to actually develop coding schemes for the real channel that we have at hand. Okay, and essentially, if you have an arbitrary network, if you're given channel gains, essentially, if you recall, with the actual channel model was this real addition with scalings. We can translate these to how many MSBs are above the noise floor, and essentially create for any arbitrary network this kind of a model. The first question one can ask is, if you're given an arbitrary network, say a single flow, what is the best amount of, what is the best information rate you can send over the network? And for that, you essentially think of an algebraic representation. So I'm going to define what's called a cut in the network. A cut in the network essentially separates nodes. So this is a node cut. It says, suppose it separates S, A1, A2 from B1, B2, and D. And essentially, you can think of this whole set of nodes as one cluster, another set of nodes as another cluster. So in a sense, this looks like multiple transmit antennas and multiple receive antennas. So we will see how this connection comes about. So to digress very quickly, let's look at what multiple antenna channels look like. So if you have M transmit antennas and say M receive antennas, for a point-to-point channel, suppose all these antennas are co-located, then you essentially can use these antennas to coordinate to send information. So for example, one of the breakthroughs that happened in the mid-90s was the realization that if you have M transmit antennas and M receive antennas, you could in principle get effectively M degrees of freedom, or M flows or streams through such a network, such a channel. So you can actually use this multiple antennas for multiplexing gains or for increasing robustness to channel fading. That is, you could have a lower rate, but even if many channel gains are bad, you can still get the information through. So what was established was the multiple antenna capacity, which is if you have a set of transmit antennas and a set of receive antennas, the capacity is related to the log determinant of the channel transfer matrix. Now, I've essentially been a bit sloppy here in the sense that you can actually do better than this. You can actually do, if you know the channel, you can essentially get H, Q, H star 1 by, so let's say it's noise is unit variance, and you can also get to maximize over your transmit covariance matrix with a trace constraint, which says what's the power. So you can actually do that. What I've written on the left side is really saying that you say Q equals the identity. And that may not be the optimal. It's not necessarily the capacity, but it's an achievable scheme. And so why is this MIMO thinking useful in our case? So one way to think about when you want to send information over a network is that you have a set of nodes that you can try to let cooperate. And you can think of all of them being transmitters. So the MIMO takes advantage of the fact that all transmitters have access to this message, and the received information is pooled to decode the message. In a network, that is not quite the case because the transmitters are not co-located, which means that the information needs to be communicated between the transmitters. And the receivers are not co-located, which means in some ways to do joint decoding, you really need to communicate as well. So that sort of leads to the intuition for what is the best one can hope for doing. So this is the cut set bound, which can be interpreted in terms of essentially MIMO. So one way to think about the cut set bound is saying that I cluster the nodes. The best I can hope for is essentially clustering the nodes. Clearly, the source has to be part of the transmit cluster. The destination has to be part of the receive cluster. And if you think about this, then you can essentially say that this can be sort of a network-wide MIMO. And in any cluster, the best one can hope for is the MIMO capacity of that clustering. And essentially, the cut set upper bound essentially says that the minimum over all such cuts, the MIMO capacity is essentially an upper bound. That's a very rough way of explaining the cut-set bound without actually deriving it in a precise way. Okay? So more precisely, the cut-set bound essentially says that if you have a network which has n nodes, then you get to minimize over all cuts where omega is, as I said, a cut where omega, the source is part of omega, the destination has to be part of omega complement. It's the minimum over that, and the maximum of, essentially this is saying that it's the mutual information, it's essentially the MIMO capacity. That's effectively what it is. For deterministic channels, this simplifies. So if you just expand the mutual information, since if you give me all the signals, there's no more entropy left for a deterministic channel. It's just the conditional entropy. So the second term is 0. And for linear deterministic networks, the optimization actually is even simpler. It just translates to the rank of the transfer matrix. Okay. So given this, so basically you should keep this in mind. We'll come back to essentially comparing how good many of the schemes are with respect to this generic cut-set upper bound. So what are the known cooperative strategies? So for example, one of the first strategies that was suggested in a classical paper by Algamel and Cover was what's called the decoding forward strategy. So the decoding forward strategy, which is done for the 3-node network, says that the relay node tries to decode the transmit message. So in other words, if the relay node is able to decode, effectively you can create this transmit cluster. So they can coordinate. So the advantage is that essentially you can create a 2-antenna transmit, 1-antenna receive through if the relay is able to decode. And in some sense, this is optimal if the transmit cut set is really the bottleneck. The disadvantage is that you're asking for more than what the problem definition is. The problem never asks for the relay to decode, so that might actually cause a problem. And in fact, if this cut is not the bottleneck, then actually it does not achieve the cut set bound. So essentially that's one issue. The other scheme suggested in the same paper by Algamel and Cover is what's called compress and forward. And here, essentially the relay does not try to decode. It just takes whatever signal it gets, quantizes it, and then sends the quantized value more efficiently over to the receiver. The advantage is that, in a sense, approximately, you can, if the quantized value is received at the mobile unit, approximately you can create this receiver cluster, which means that it's like a 1 transmit, 2 receive MIMO, if you wish. But essentially, the disadvantages are, in some sense, it of course doesn't decode, doesn't clean up the noise, and it does not. If the transmit cluster was the bottleneck, then of course this is not what you should be doing. Amplify and forward, which is something that actually has been there well before in fact, even network information theory was started. Even in the 50s and 60s, amplify and forward was there. Essentially, they're called repeaters. They used to be called just repeaters. And it just amplifies the received signal and sends it out. And it's very simple. That's one advantage. And but essentially, it does not. It's not something that is sophisticated enough necessarily to capture any of the cut-set bound intuition that we have. Okay, and so the deficiencies are that, in a sense, you could create networks and situations where all these schemes could have an unbounded gap to the cut set. So the basic question is it that the cut set bound is very loose? That is, can we solve? Is it true that essentially all these schemes are actually okay, but the upper bound is not very good? Or is it that we are missing opportunities to significantly increase the network capacity? And can we develop strategies that are essentially robust? That's sort of an additional question. So here is the first sort of intuition to this. If you take a network, which we call a diamond network, here's a base station, 2 relays, and a mobile unit. Here's the linear deterministic model. In a sense, the cut value is here 3 because this is broadcast, which means that these are common bits. So essentially, only 3 bits can go over this cut. Only 3 bits are essentially received over this receive cut. So essentially, the cut set bound essentially is 3. And essentially, what we're saying is that the one strategy that essentially gets you through 3 bits is that this relay is the only one which sees the blue bit. It is responsible for the blue bit. And this relay is responsible for the 2 green bits and therefore can deliver all 3 bits to the destination. There are many, many strategies that will achieve the cut set. But effectively, we will actually prove this more precisely in a minute. But if you go to this particular case, the cut set bound is achievable. If you go to more complicated networks, again, where one can prove that the cut set bound is achievable. And the questions that we will ask is this true for arbitrary deterministic networks? What is the structure of the optimal strategy? Can we use insights from the deterministic analysis for Gaussian? And so on. All right, so now I will start to state the results and prove it. But before I do that, maybe this is the first time if you have questions or anything that would be useful to clarify, I'll be happy to take any questions right now. Are there any questions? So from here on, we'll start to look through doing proofs of these results. Any questions at all? All right, okay. So it would be useful if I can also pace myself depending on how people are feeling, because I can go slower, faster, or at the same pace. So feedback is always very useful. Okay? All right. So the first result we will prove is for deterministic relay networks, which is saying that for a general deterministic relay network, we can actually achieve a rate which is the product of all product distribution and minimizing over. So the form that you see is very similar to the cut set bound, except that the optimization here, so in the cut set bound, if you recall, the cut set bound, in the deterministic case, you had maximize over px1 through pxn, min over all cuts, h of y omega complement given x omega complement. So if you look at the two screens, you can see that what we are saying is that what can be achieved is clearly smaller than this because you have a larger optimization space, but the optimization function is essentially the same. Okay? So that's basically the one result we will prove. An immediate consequence of this result is that if you take linear deterministic networks, we know that the optimization is from a product distribution, and that actually means that for a linear deterministic network, we would have it coincides with the cut set bound, and therefore we have a characterization for linear deterministic networks. And so we have for linear deterministic cut set models, the cut set bound is achievable, and you have a max flow min cut result. And for graphs are actually a special case of the linear deterministic model. So it actually also recovers. If you look at the multicast case, it actually recovers the network coding result. So when we prove this, we'll actually also prove the network coding result on the way. So here is the proof. So we will do this just for simplicity for what are called layered networks. So layered networks are the following. You have a source and a destination which are connected through relays, but any path you take from the source to the destination has the same, in some sense, path length. So if you look at this case, from going to source to the destination, you have 3 hops in any way you want to go, from A1, B1 to D, A1, B2 to D, etc. Now, this is really not a restriction, but it helps to sort of illustrate the ideas more easily. And we will see how to extend these ideas almost directly to arbitrary networks. And so here is the strategies that what we'll consider. Every source essentially takes the message, maps it onto a block length of t. Now, what the relay does is that it takes whatever it receives, and instead of trying to decode or trying to figure out what the message was, it basically chooses a mapping onto its transmit signal. This mapping is which we denote as Fj. For linear deterministic networks, it's just a random linear combination. For arbitrary networks, arbitrary deterministic networks, we will illustrate this in a few minutes. So for the linear deterministic network, what the relay does is it gets a signal, it maps it with a matrix Fj, and translates it into the transmit signal. And here's a sort of a cartoon illustrating this. So if you have a source, it sends out a certain signal. Some of the bits are received at the two relays, and what this relay, for example, does is takes whatever is received, takes a linear combination, and maps it out. And whatever it receives, these guys do the same, and so on. So effectively, you get an overall linear transformation from source to destination from here. Now, is this clear, or is this too fast, too slow? Is that fine? Okay. All right. So how do we analyze this? The analysis is essentially, I'm just going to make it simple through the layered networks. The simplification is that suppose you have messages W1, W2, W3 that you want to send from the source. At the first time instant, the source sends something which is a function of this message, and relays A1 and B1 are listening to it. In the time block 2, so we're going to operate, the whole operations are going to be in blocks of time. So in other words, every node is really operating over t time instance. This is really the block of operation. And what we do is that at every at time block 2, A1 and B1 are going to send something that is a function of what it received in the previous time block, and that gets received at A2. And in time block 3, A2 and B2 finally send something which is a function of message 1, and the destination gets to hear it. Now, in the meanwhile, in time block 2, W2 was sent from S to A1, B1, etc. So there's a sort of a pipelining of the messages. That's really what makes thinking about layered networks easier. Okay, so therefore, at every time block, the destination is receiving a function of only one of the messages. So we can focus on only one message and think about essentially analyzing it for that. Okay. So for analyzing it, we have to have a notion of distinguishability. So suppose we have the message W, which is the correct message, and we are asking for what is the probability that an error occurs. Now, one would immediately think about where is probability coming in. So at the moment, remember, we are talking about deterministic networks. So there is no noise in the network. So the first question is, where is probability? The probability really comes from the fact that in order to design the maps of the relay, we don't. If we were infinitely clever to design the maps properly, we would have a deterministic construction. But what we are really doing is a probabilistic argument. That is to say, we will choose a mapping which is random, and we will, in the classical information theory sense, just say what is the probability of error averaged over all such random choices. And if the average over these choices, the probability of error goes to 0, then there should exist a transformation that works. So essentially the probability really comes exactly because of design choices, not because of the channel. We will actually, when we do the noisy case, we will see the effect of both. So since the whole network is deterministic, we can define a notion of distinguishability. In other words, nodes that, so if everybody knows all the mappings and all the transformations, so a node, when it receives a particular signal, can actually say whether a message W was, so it can say what is exactly the received signal it will get under a specific message W, because it's completely deterministic. So it knows, it can predict if the source sent this message, what I would receive. Is that clear? So the only way a node is confused between two messages W and W prime is if it got exactly the same signal under both the messages. Right? That's the only way it can get confused. So we define a notion of distinguishability, which says that nodes that receive distinct signals under W and W prime can actually differentiate between W and W prime. And if they, of course, receive the same signal, they cannot distinguish. So they will be confused. Is that clear? Because this is a notion that we will use not just here, we will use it for the noisy case as well. So this is important to understand. Is that fine? Okay. So essentially one can say that the probability of error that is mistaking W prime for W is all ways in which this event can occur. That is, you want to make you don't really care if nodes in the middle of the network are confused or not. All you care about is if the destination who really wants to decode the message is confused or not. And so all ways that can happen is nodes in omega, where omega is essentially the set of nodes so omega is the set of nodes in the network, which is U, such that S, the source, is an element of omega, and essentially D, the destination, is not an element of omega, or is an element of omega complement, if you wish. So omega is a set which is defined like this. So all possible ways in which you can create in a sense what's called a cut in the network. So you can think of this as a source destination cut. So now what you can how can you actually analyze this? So we'll just do a simple example to analyze this, and we will carry this example through to the noisy case as well. So if you notice that we have a summation over all possible cuts, this probability. So we will actually just examine one such cut, and that will enable us to analyze this. So to look at this particular cut, so if you think about it, so let's say omega in this case is S, A1, A2, and that means that they can distinguish between W and W prime. And omega complement is B1, B2, and D. So the error event is essentially that somehow you have chosen the maps such that all the nodes in omega complement have exactly the same received signal under W and W prime. And that's basically what we are trying to analyze. So what is the probability of that happening when we have this relay transformation? So recall that the relay transformations were at every node in the network. Xj was just transforming whatever it received through a linear map onto the transmit signal. So as a consequence, the probability of error is the following. So it's a probability that YB1, so here B1 is the node here, is confused, which means that YB1 equals YB1 prime. This node is confused as well, which is YB2 equals YB2 prime, given that this is not confused and this is confused. That's essentially what this is saying. And finally, YD is confused, destination is confused, which is the most important one, given all the previous things. That is, A1 is not confused, B1 is not confused, A2 and B2 are confused. That's really what this is saying. And so essentially you can analyze each of these terms. And so the first thing to observe is that if because of the structure of the map, because we are actually using the map where whatever is transmitted is just a function of what is received, regardless of how it came about. It's uniformly at random. So Fj IID uniform over. So it's a matrix that's IID uniform over the finite field. So essentially it's uniformly at random mapping whatever it's received. So which means that it has essentially lost effectively the memory of what had happened in the past. So it really does not matter if at this stage, if A1 was not confused and B1 was confused, for D, all that matters is what's happening here. All the memory from before is gone because of the uniformly at random maps. So as a consequence, you essentially get a Markov chain relationship. You drop the conditioning. So now, essentially, it says that if you have, so I'm just rewriting the same probability. So it's essentially asking the question, what's the probability that the first term, that is YB1 and YB1 prime, are confused? It's probability that the signal that you chose at the source for W and the random signal that you chose for the source at W prime is such that it's in the null space of this matrix. Recall that if you look at what the GSB is the channel transformation. Oops, I have it here. Where did I have this picture? Yeah, there you go. GSB is essentially so if you look at the source to the relays, what is received is a linear transformation of what was transmitted. That's really what we are using. And it's just saying that if it's in the null space, and that essentially is exponentially small depending on the rank of this matrix. Yeah?
Is that Kronecker product because you are using blocks?
Yes. So the Kronecker product comes because you have the transformation, that is Yj is equal to G summation Gij xi is for every time. We are using blocks of length t, so the same transformation occurs over. That's exactly why you get a Kronecker product. So therefore, essentially here you get this is a block. This is like a vector which is stacked up. This is of course the Kronecker product block diagonal matrix. Is that clear? Okay. So essentially it says that the only way this can happen is really that you have to make sure that this vector lies in the null space of this. And that's just a counting argument that gives you this probability. And in exactly the same way, we can see that essentially for the second one, again, it has to lie in the null space. It corresponds to the rank. And from this, if you just put this together, essentially the probability of this happening is really exponentially small depending on the rank of the entire transformation. That's really why this is happening. Okay? So therefore, you get P, which is essentially the probability of mistaking W for W prime for that particular cut, is really exponentially small depending on the rank of that transformation for that cut. And therefore, the probability of error goes down like this, summed over all omega. And therefore, if your rate is smaller than the minimum, because the dominant term in this expression is really the smallest omega, happens for the smallest omega. Is this clear or fine? Okay. So essentially, this proves that for this particular example, at least, the minimum over all cuts, the rank of g omega complement is achievable. Now, it turns out that what we did for this example is not something special. It is really true for every such layered network. You can just, the analysis is exactly the same. In fact, you don't even need to write, you just write down the transformations in a block and do exactly the same thing. So this essentially proves the result for linear deterministic networks. Any questions before I do the same for, yeah?
So what is the intuition that when we are confining ourselves to linear network, like linear deterministic network, then the distribution that achieves the cuts or achieves the capacity is like uniform?
The intuition is the following. So what if you look at any finite field, the maximal entropy occurs when you have uniform. Okay? So now if you have any linear transformation, if you have an input that is uniform, the nice property that a linear transformation has is that the output is also uniform in the range space of the linear transformation. So therefore is maximal entropy. And if you notice that the cut set was essentially saying something about maximizing the entropy, and that's the reason why. Is that clear? Yeah. All right. So in fact, the proof that we did for the linear case is actually almost exactly what you would do for the general case. So again, if you take general deterministic networks, now it's not linear anymore. So for general deterministic networks, so here this was the transformation you did for linear deterministic. What is the transformation you do for general deterministic? What you do is the following. Again, you use the same intuition. Suppose you have a node which has received y of t. These are the possible received signals. You map it, so you essentially choose a distribution, say pxj, for every node j. So that induces for it a typical set, SS or a code book of for every node in the network. So let's say this is the code book. And so what you're doing is that what you will do is effectively map every received signal, map it uniformly at random. You map it uniformly at random to the transmit codebook. That's really the coding scheme. So the analogy is that in the linear deterministic case, you're doing exactly the same thing. Whatever you receive, by choosing a IID matrix here, what you're doing is that you're uniformly at random mapping whatever you have to the transmit sequence. But this transmit codebook has been chosen from a uniform distribution effectively. Here, the difference is that the transmit codebook is chosen according to a particular distribution, not necessarily uniform. All you're doing is that you're mapping whatever you have received uniformly at random to this transmit codebook. Okay? So that essentially means that, again, the same kind of property. The only property we used in the linear deterministic case was the sort of a Markov chain or memoryless property. It did not matter where this whether A1 and B1 were confused or not. What matters for D is whether A2 and B2, what the state situation is. That's really the same calculation that we're doing here. Now, the probability of that occurring, so if you think about this, it's really saying that if you have a source, this is really saying when is this node going to be confused. It means that when you take two independent sequences, what's the probability that they will result in something that is jointly typical? This is almost a standard information theory calculation, which says that the probability is exponentially small, and the exponent is just the mutual information. Okay? In exactly the same way, for the second layer, essentially it says that this one is not confused, but since B1 is confused, which means that it has received the same signal under W and W prime, essentially what it transmits under W and W prime is also going to be exactly the same. So exactly like essentially like a multiple access channel, it says that the probability that B2 is confused is the probability that, so it's saying that the probability that B2 is confused is, this is X A1, X B1. So if B2 has to be confused, this is exactly the same as, so if you put primes, this is X, exactly X B1. So this is the probability that something that has been generated in this manner, that is P XA prime is A1 prime, is generated independent of XA1. And so it's saying that something that has been generated like XA1, BX B1, Y B2 behaves like BX A1 as if they had been generated together. So this is one fact that we will use repeatedly. So let me actually. So in some ways, in information theory, there's one lemma which is repeatedly used, which is the following. So if you generate a code book, or let's say random variables, random variable IID according to say PQ, and we ask what is the probability that it is typical with respect to P. So let me call this FQ. What's the probability that the generated sequence is typical, which means it passes any statistical consistency check for being generated as, say, f of p. So it looks as if it has been generated with a distribution p. And that, if you have n length variables, or in our case t length variables, this is basically like 2 to the minus n d pq. That's really the basic theorem that is used all the time. So now if you now use this, if you think about this, the probability that you generate something like this, looks like this, is like expected log p xa1 xb1 yb2 divided by p xa1 p xb1 yb2. So this is really like the multiple access channel with one of the things that is right. And so essentially this is, so if you look at this is n, this is dpq, right? This is essentially what will be the dpq for this case. So this will be 2 to the minus, so I said n, so I should say t, I of x a1 yb2 x b1. That's really what this is. And in our case, since all the relays, the distributions that we are choosing here are product distributions, so we are using pxj are independent across nodes j. This will essentially become 2 to the minus t I of xa1 yb2 given xb1. And that's really what we are writing on the left side. So this is, if there's one thing that you'll always remember from information theory is essentially this relationship. That if you generate code books or something which is from one distribution, the probability that it behaves like another distribution is exponentially small, and it's related by its callback libraries. And that's something that we will repeatedly use even in the noisy case. So that's all there is to this. So that's basically all that this calculation is doing. And once you have that, then if you just put them together, you'll see that exactly the same way as we did for the linear deterministic case, that we get the rate, which is the conditional distribution. But because we chose each of the relays to have a product distribution, you can get to optimize over it. And that's essentially what it is. So that proves the layered case for deterministic channels. Okay? Any questions? All right. And for we did this for layered case. We can actually do this for arbitrary networks. So suppose you have a network which has a non-layered network, which means that to get from the source to the destination, you can do multiple paths. You can essentially create a new network which is layered by doing time expansion. This was a very neat idea that Raymond Young did in network coding, which can be immediately applied. So essentially, one of the things that matter here is that now in the time expanded network, this is saying that you want to essentially send messages over blocks. So it's essentially you're creating blocks of blocks in order to prove this result. And this essentially works out, and you can actually, I don't want to go into the details of how this works, but you can look at a reference that I can point you to that proves this. So essentially the same, once you have the result for the layered case, you can extend it for arbitrary networks. Okay, so that essentially, the summary for deterministic networks is that now we've essentially, with this, you can prove this result. So if there's, yeah.
Is there any result for the capacity of the general deterministic network?
So we mean that for general deterministic networks, so there is the only capacity known for general deterministic networks is when there is only broadcast, what are called RF networks. Of course, if it turns out that your functions are such that, like it happened in the linear deterministic case, that the product distribution is the optimizing distribution, again we have it. But if not, then, or you could look at special networks. So for example, for special networks, you can actually get the right answer, but not for arbitrary networks. Okay? So what I will do next is essentially do the noisy case, and after that we will take a break. Okay? So the main insights from the deterministic case is essentially to forward evidence rather than decode, cluster for noise, and directly map onto the transmit sequences. That's really what we did. So this leads to what's called the quantized map forward strategy. So the quantized map forward strategy is the following. Any relay doesn't try to decode. It quantizes the received signal, say for example at noise level. So let's not worry about that for the moment. The main thing is that it maps its received signal directly onto the transmit signal. And essentially all the relays operate independently and forward. The decoder, which we will specify more precisely in a second, utilizes the structure of the mappings and decodes without requiring to know all the quantization code words at the relays. And for this, we can essentially prove a approximate max flow min cut result, which we will do in a minute. But essentially, it says that the earlier schemes that I mentioned, the compress forward and the decode forward, etc., they could be arbitrarily far away from the cut set, but this says that you can actually achieve within a bounded gap. And exactly the same will work for multicast, and essentially it philosophically generalizes network coding to the wireless case. Okay, and it has many advantages. It has sort of a universality property, which says that since you're doing direct mapping, the relays do not really need to know what is the other parts of the network. They do not need to know the overall network topology and the channel information. It works for full duplex and half duplex networks. Half duplex is most current wireless phones and devices cannot transmit and receive at the same time. So essentially this can also work. It works for multiple antennas, and it also works for outage and so on. So we'll actually talk about many of these things. There's a very nice extension of this, the QMF, to memoryless networks by Lemma et al. They call it noisy network coding. There's a nice extension to essentially eliminate some of the things, components of this to using short block lengths by Kramer et al. And there's a modification of compress and forward and using algebraic flows, which also gets the same rates. These are more recent extensions that have been done. Okay, so let's do the proof for this result. So once we have understood the deterministic case, essentially the same kind of ideas will enable us to prove the noisy case. So here's the scheme. So in exactly the same way as we did for the deterministic case, we map the messages onto the transmit sequence. But this time we do it, since we're doing Gaussian networks, we're going to use a Gaussian codebook. Okay, so we uniformly at random, like any point-to-point channel, you uniformly at random map it to a Gaussian code word. Quantization. So what is the quantization? So this should be plus. Sorry, this should be. I know actually this is the optimal distribution. Actually, I'm going to use a suboptimal input distribution, quantization distribution. But nonetheless, what we will do is in the quantization, we will generate a vector quantizer with a certain distortion, and the mapping and forwarding. So in a sense, the difference in what we have done from the deterministic case is really in the quantization. We quantize the signal rather than mapping the signal directly onto the transmit sequence. And the reason for this quantization is that you want to minimize conveying the noise forward. And the mapping forward is essentially saying that you generate the transmit sequences, IID, again as a Gaussian, and you associate uniformly at random each of the quantization code words to the transmit sequence. Okay? So it's essentially almost exactly the same idea as we did for the deterministic case. So you can think of essentially y hat of j, block length n, x of j, and if these are the quantization code words, they are uniformly at random mapped onto transmit sequences. That's really what's happening. Okay? So here is the quantizer, and this is where I want to make one simple point. Why I'm going, for simplicity, I'm going to use not a rate distortion optimals quantizer. So what does a quantizer do? It takes the received signal, maps it onto a code book of quantization sequences such that a distortion criterion is satisfied. So this can essentially be represented by a test channel The optimal, for the Gaussian case, the test channel, that is basically saying what is the distribution. So you're using, in the rate distortion codebook, is generate 2 to the, I'm using n, I guess, in this part. So 2 to the NRI code words, y hat j. If you want 1 up to y hat j, 2 to the n or j, for the jth. So you're creating this many code words. And what does rate distortion say? That if you get receive yj sequence, find y hat j kj such that the expected distortion between y hat and y is less than equal to what you desire. And this expected distortion in our case is just 1 over n summation the norm difference, yj of t minus y hat j of t squared. That's really the normalized L2 norm for the Gaussian case. So standard rate distortion says that essentially if you use a certain input distribution for a certain distribution for the codebook, that as long as you generate more than I of yi hat, then you're going to be able to successfully quantize. Now here's why I'm saying I'm using I'm being lazy and not using the optimal quantizer in order to make my life easier. So I'm choosing a quantization distribution which is y hat equals yi plus qi. In other words, I'm setting in the test channel beta I equals 1, and of course the distortion is to be a 1 because I'm just saying it's noise level distortion. So I'm going to get a rate which is log of 1 plus the variance of the source. If you look at the optimal rate distortion, it's actually going to be without the 1 plus. It's just log of sigma I squared. So I'm actually generating more code words than necessary just to make my life a bit easier. Okay? And essentially, if you look at the implication of this test channel, this almost looks like the original channel, except that you have one additional noise term because of the quantization. That's why I made this, makes my life easy. So essentially, it's like a noisier original channel. That's all. Okay, very good. So how does the destination decode? The destination has to consider all plausible sequences. So it receives a signal. It's trying to figure out what the source said. It knows all the mappings that all the network does. It knows all the quantization code books, etc., and the transmit code books. But it doesn't know what each relay got. It can only guess. So it forms hypotheses. It says, okay, suppose each of the destination got this. Does this form a consistent set? Consistency in our case will be checking for joint weak typicality. Okay, so what does consistency check mean? So it's a Gaussian channel. So if you notice, that's the reason why this nice form where you have y hat, which is almost like the original channel, except the additive noise is larger, becomes nice. Because then what I will do is the first part. So the first and the second are just saying that what is received has the right marginal, weak typicality marginals. The most interesting one is only the last one, which is saying the following. If you notice the test channel, it looked like yj hat is summation I element of, say, the previous layer. we looked at scalar channels, so let's just say xi, xj plus qi plus zi. I'm just going to call this, say, psi j. So this is just some effectively larger noise. I don't worry much about that. So now all I'm looking for, and it's Gaussian because the test channel, the quantization noise is Gaussian and the receiver noise is Gaussian. So this psi j I'm writing down is still Gaussian. So what it's saying is that what is a natural consistency check? It says that I take this hij xi, and this is like Gaussian. The reason I'm choosing the quantization level is 1, so this has variance 1, this has variance 1. So this looks like Gaussian with variance 2. I want essentially that I take the difference of my quantized output and what my hypothesis of what could have been transmitted, or my hypothesis of what was the quantization value and what could have been transmitted, and they should be actually close with respect to sigma I squared. That's basically all that this consistency check is doing. And so all you're doing, the joint consistency check, is essentially looking at across all these layers. So what the destination does is that it says, okay, I don't know what quantization indices were received at every node. It says, okay, let me check for a candidate set. Does this satisfy the consistency check? Because for a particular choice of KIs that it takes, all the quantization indices, I can check if they will lead to this joint consistency or joint weak typicality, which is just this check. And if it does, then this message is a plausible message. I cannot eliminate it. So the error condition is essentially that, of course, the correct message is not part of this plausible set, and that an incorrect one is part of it. That's the natural way to think about error. And if you want to bound the error probability, it's exactly the same. For the deterministic case, this was immediately 0, because the correct one will always be jointly typical, or will be correct, because there's no noise in this network, right? When there's noise in the network, you could, in principle, have atypical noise. So that's why this error could occur. So this is a term that did not occur in the deterministic case. This is a term, of course, which effectively was in the deterministic case as well, but it'll take us a little bit more work to analyze it. That's all. Okay? And the way you analyze this is by the following. So let me make this full screen so that it's clearer. Just 2 more slides to finish this proof. So what is the probability that an incorrect code word is actually going to be in this list? So that means that there exists some hypothesized quantization indices such that it passes the consistency check. So that you can bound by summing over all possible quantization indices the probability that a particular choice passes it. Is that fine? So I'm going to basically condition on the correct message, the correct one producing KIs, and KI primes are the hypothesized ones. And I'm going to write conditioning based on this. So now you'll get a form which is almost identical to the deterministic network, which is that the probability of this error occurring is essentially the sum over all possible cuts. The additional thing that we have over the deterministic case is the sum over all possible quantization indices. The probability that your hypothesized thing passes the consistency check. If Ki prime equals Ki, it's exactly like being confused. And if Ki is not equal to Ki prime, then it's like this node is not confused. It's exactly the same analogy. Okay? So the way, if you think of the event that a particular node passes the consistency check as we write it as Qi, then that probability can essentially be written. So the error probability is saying that for all nodes in omega complement, this happens, and all nodes in omega, it happens. I split the error into two parts. Just write down this probability into two. This times the probability that that happens in the non-confused set condition. This is just base rule, nothing else. I've not done anything. There are two extremely simple lemmas that I will show in a minute, which is an immediate consequence of a very simple observation that will enable us to complete the proof. The probability that a node is the set of nodes are confused is exactly like the remember when we said that it's the probability that something that is confused is like the mutual information. It's almost exactly that, except that you get an additional term which is due to the fact that you're dealing with quantization. There's additional noise. Okay, so that's basically what accounts for this. And the second one is that this essentially says you are going to pay for the fact that you have many, many candidates. The fact that there is a list of possibilities. And that essentially will cause this gap. So if you just use these two lemmas, if you write down the error probability, so you essentially get the first lemma. It says that this term is upper bounded by 2 to the minus n log determinant minus half omega log half of omega. That's basically the first term. You sum over all ki's. The second term essentially gives you one more half n log omega, and that's why you get half plus half is 1. That's essentially this. And once you have that, the error probability is essentially that as long as the rate is smaller than the minimum of this, your error probability goes to 0. So essentially what it says is that you can achieve a rate which is essentially like what looks like the MIMO capacity for that cut minus a gap of the number of nodes. Okay? You can also prove that if you used an IID, the gap between that and the cut set is at most the number of nodes in the network. And if you put these two together, immediately you get that the rate that you can achieve is within a gap of at most 2n, where n is the number of nodes in the network. Okay, so all that really remains. So basically, these two are the. If you believe these two lemmas, you're basically done immediately. So how do you prove this lemma? And it's really a very simple consequence of what is a quantized channel lemma. The quantized channel lemma says is something that is intuitive. It says that if you take a channel, say in this kind of a channel, and you take the output and you quantize it, and you want to essentially look at what can the quantized output say something about the inputs. Okay, so suppose you just take IID Gaussian code words and send out at these for U1 and U2, and you quantize using the kind of quantizer we used, which is a Gaussian quantizer with sort of a looser quantization. Then what you can show is the first thing. Remember I said that the first term here that should be small is really a consequence of the fact that the correct one will actually be jointly typical with what is received. So that's really a consequence of what's called the Markov Lemma, but this can actually be proved for the Gaussian case very simply. It says that if you send out signals that are corresponding to the correct ones, and you're testing for joint consistency or typicality between what the quantized output is and the correct ones, that will be true with high probability. That's the first. The second one says that if you take something that W1 prime, which means that this is independently generated, but W2, which is correctly generated, then the probability that these will pass the consistency check essentially is exponentially small, the exponent being like the log determinant, and this is really the quantization gap. That's just the quantization gap. And the third is essentially saying that if you take an independently generated quantized output, then the probability that all of them are jointly typical is essentially it basically, this result is actually almost, it's exactly the same DPQ result that we've been using. So the last one says that you take y hat j, which is independent. So you have y hat j equals 1 through m, each of which, each quantized independently. So it's asking if you generate PU1, U2, and PY1 hat product, PY hat M, independently, what's the probability that it will look like they are generated together? And that probability is exactly like 2 to the minus n summation h y hat I equals 1 through m, minus h y hat 1 through y hat m, given u1, u2. That's exactly what this is. This is exactly like the DPQ lemma, if you just apply it directly. And that, if you just plug it in, you get this result. And with this, the lemmas I stated is an immediate consequence of these two, this observation. So all it's saying is that something very intuitive. It's saying that if you take a quantized output, if it was not a quantized output, then all these are fairly simple. It's standard. It's all it's saying is that when you take a quantized output, all the things that you expect will also occur. That's all. Yeah.
So here ki prime is another index indifferent from ki.
Yeah, it's saying that something which is independent, it's something that ki prime is not equal to ki, the actual one. What is the probability that independent quantization index it checks with the consistency check?
So it is actually the index of one of the quantized vectors?
Yes, exactly. That's all. So once this happens, this is essentially, this proves the result. So I think this is a good time to take a break. The result that with the scheme that we set, which is quantized map forward, we can achieve a rate which is within essentially at most 2 times n for the real case, 4 times n for the complex case within the tacit bound capacity. And the scheme itself is very simple, as we said, which is you quantize at every node and map it forward regardless of every other node in the network. And the analysis was basically based on the decoders doing the decoder doing a consistency check, and the error probability is bounded by a simple lemma, which is based on the what we call the quantization channel lemma. And that essentially is all I wanted to say about this the noise, the single flow network with Gaussian codebooks. This can actually be extended using lattices, essentially with instead of using Gaussian codebooks, you can actually use lattices completely. And the gap and etc. is exactly the same as the Gaussian codebook. And the only interesting thing I wanted to say was about the picture of how these lattice constructions work. Maybe I'll go through this very quickly. So I want to get to the point that, okay. So the lattice construction works the following way. The quantization is essentially using, instead of a Gaussian codebook quantizer, there's a lattice quantizer. The mapping at the relays is actually becomes very simple. So what it does is the following. If you take whatever you see, yj, and you quantize it to yj hat using a lattice, lattices and linear codes have a sort of a one-to-one relation. Lattices can be constructed from linear codes. So what you can do is, when you get the quantized value, you can essentially get a binary sequence which is corresponding to a linear code underlying the lattice. So that's essentially what this operation does. So essentially it extracts the binary representation of the lattice quantization point. And then what you do is you multiply it with a, just like we did in the linear deterministic model, you multiply it with a random matrix over the finite field. And then you take that binary sequence output and then you lift it up to construct the other lattice. So essentially the other lattice point is constructed through essentially a completely finite field operation. So this makes it analogous to the linear finite field, but through lattices. Okay? And the way you analyze it is essentially that lattices and Gaussian are actually very close if you go to large dimensions. You define the consistency check exactly like you would do for the Gaussian case. And the analysis exactly follows like the Gaussian case, except that now you basically take the high dimensions lattices essentially get Gaussian approximation. So essentially you can prove the lattices result exactly the same way as you did for the Gaussian case. So that's one thing that I want to mention. The second thing I wanted to mention very quickly was that you can also, for very special networks, get approximations that are independent of the number of nodes in the network. So for example, in this parallel relay network, you can essentially get an approximation that is for very special cases like the symmetric case that is independent of the number of relays in this network. So the reason to point this out is that for special networks, you can actually get very, very strong, much stronger results. But the point that we made earlier is that for general networks, it's much harder to do this. And finally, you can actually also implement quantized map forward using iterative codes. And the way you do that is by essentially each of the maps at the relay, instead of being either a lattice quantizer or a Gaussian quantizer followed by a uniformly random map, you replace it by a DP sequence. Okay? And if you do that and you use a belief propagation technique to decode, exactly sort of similar spirit to how we did the decoding for the Gaussian case, you can actually get results which are actually fairly good in comparison to what the theoretical bounds are. So in other words, we can go from the theoretical understanding to try to develop structured codes to try to match this. That's basically all the point I was trying to make. Okay. So the summary is that it enables distributed operation that supports multicast, approximately achieves net capacity, and it has some promising performance with iterative code implementations. So we are done with single flow. I'll very, very quickly do the two Unicast and then go to source coding problems. So the two Unicast problem essentially is the classical example is the interference channel. We have two sources, two destinations, and interfering links. And the current solution, of course, is to orthogonalize. There's a lot of very interesting understanding about how to do things when base stations cooperate, etc. A breakthrough result by Atkins Wong said that for the interference channel, you can actually get a constant bit approximation, and that the capacity scaled in terms of degrees of freedom actually has this W curve, which also can be understood from the deterministic model. And the main observation I want to make here is that without transverse cooperation, the interference channel is fundamentally limited by the message interference. That is, if you were on your own, you would get 1 degree of freedom each. But because of the presence of another user, unless you are in the very high interference regime of no interference, you are always below your 1 degree of freedom. So you essentially lose a little bit. So the question is, can relay center situation? And one way is to think about the two-stage relay inference network. So you basically create two unicasts with relays in the middle, a layered network. And the question is, can you actually do, is there a new inference management scheme that you know? And we just consider the ZZ network. So essentially ZZ means that the crosslink is absent. And if you look at the deterministic model, I just want to illustrate the idea of what might happen. Suppose you want to send 2 bits from the source. So the cut set from source to destination is 2 bits, S1 to D1. And from S2 to D2 also you could potentially get, in fact, in this case, 3 bits across if you didn't have any interference. But since there is interference in this case, so the question is, how much can you do? So suppose you send A1, A2 here, B1, B2 here. What relay 1 sees is A1 plus B1, A2 plus B2. So it cannot decode anything. Relay 2 gets B1 and B2. Now what it does is it forwards B1 and B2, but at the same time, the same B1 and B2 can essentially help in eliminating B1 and B2, that is cancelling interference over the air. This is essentially what we call interference neutralization. This is a signal level cancellation. So with this, you can actually get 2 bits across from source 1 to destination 1 and 2 bits across from source 2 to destination 2. Okay? And essentially what you're saying is that you're making dual use for here to transmit the message as well as sort of cancelling the interference. And that's why we call it interference neutralization. And you can essentially apply this to real channels just by using lattices. And what one can prove is that with a bit of work that this is actually approximately optimal. The most important thing is that, in fact, if you look at this rate region, you can actually, with the presence of these relays, you can actually get 1 degree of freedom each for each of the users. Okay? So in a sense, if you did not have relays, you could not get 1 degree of freedom per user, but with relays you can. And there's been a lot of recent work on 2 unicast networks, which are just listed here. But most of these characterizations are not in terms of additive approximations, but really the degrees of freedom kind of approximations. Whereas this was really an additive approximation. All right? So essentially, this is all I wanted to say about wireless networks, and I want to say more things about source data compression and so on for the next hour. So if you had any questions about wireless and so on, this is a good time to ask, and then I'll go to data compression. Any questions? Yeah.
Bruce Neeson has a similar approximation model.
So he has an approximation model which extends our deterministic model with multiple shift matrices. And basically for there are 2 ways to think about this. The way you want to think about what we have done is that you take the deterministic model and you get insights to get the Gaussian, right? Now, you can also, in some particular cases, for example, for the interference channel, you can almost directly go from here to the approximation result. And what Urs and Magali have been trying to do is to see if they can use this, not just using the if you think about the deterministic model we're looking at, it's just looking at the MSBs. What they do is look at not just the MSBs, they just look at a sum of shift matrices. It's not a convolution. It's a summation of the shift matrices. It's basically instead of having a single MSB, which is like a band, which is a shift matrix. It's like a not lower triangular, but essentially fills up the rest of the matrix. Now, this helps in some sense to get some insights into how to do it for interference networks. It's actually a bit more useful, and that's exactly where they apply it. But for single flow networks, it's not that, it doesn't help very much. Okay? Even for interference networks, it depends on whether you want to do the approximation directly or gain insights. Just the MSB approximation has yielded a lot of insights even for interference networks. So, Any other questions? Yeah. Which in Unicast? No. Each of the destinations is only interested in its own message. So they could actually be a part of the message that decodes for another guy. That could be a strategy. What's that?
How the Unicast case?
Oh, in the Unicast case, there's only one message.
Yes, we will receive out of the kind of contact with all the different files. So we do not.
No, there's only one message. What you're decoding is the message, not what the relays are. You're not actually trying to figure out what quantization code the relays are. You're only decoding a single message. There's a single source in the destination. That in the very beginning I made that distinction between single flow networks and multiple flow networks. Right? This is a sort of a meta that is saying you may be relays and so on, but you are asking how many messages are being made. Any other questions? All right. Okay. So let's go to data compression and source channel separation and so on. So debatably, one of the most important architectural observations of Shannon theory is what's called the source channel separation design, which says that asymptotically, when the block length that you're transmitting becomes very large, then if you want to send a source, so suppose the source is like a video or image and so on, and you're encoding a source and you want to send it over a noisy channel, and the destination is interested in recovering the source, but perhaps with the source. Then one natural strategy is to say, well, I can do data compression and then get bits out and then do whatever I know how to do for cleaning up the noise, and then I do data decompression. That's one strategy. So this is a picture from Fano's book from 1960s, which is essentially saying that this is sort of the architecture for source channel separation, which says you separately design the source coding and channel coding subsystems. And Shannon's source channel separation result says that asymptotically there's no loss in optimality of rates in this architecture versus a joint coding architecture which does not split it into data compression and channel coding blocks. Okay? And in some ways, it's well known that source channel coding fails in networks. Point-to-point case, it's true. Source channel coding in even broadcast and correlated sources or multiple access channels is not true. So in some ways, what are we saying? We're not asking we're asking what about source channel separation. So what we're saying is that is there a general class of networks for which the separation approach is optimal? Or if not, is it approximately optimal? And in some ways, the basic difficulty is that general networks, you don't know how to even know what the channel capacity is. How do you define this source channel separation? How well it can do? And that's basically the difficulty. And so we essentially are able to answer this question in many different ways. So we start off with the root question: is source channel separation optimal? And in some cases, we can say yes, it's optimal. And can we actually characterize the individual components? We can, of course, sometimes say yes, but in some cases no, but still give an architectural result which demonstrates that it's optimal. In cases where source channel separation is not optimal, you can ask the question, is it approximately optimal? Approximately in the sense that we will define it soon. In some cases, you can actually say, yes, it's approximately optimal. And we can ask again, can we give this characterization of the individual components? The answer is yes in some cases that we will see. And its answer in some cases is, even though we are not able to give characterization of individual components, we're still going to be able to give architecture. Okay? And that's basically the sort of logic that I want to present for the next one. Okay? All right. So the central difficulty is that ray distortion and in some ways the capacity also can have some kind of curvy boundary. And basically the idea that we are going to look at is to find essentially polytopes that essentially bound this curvy boundaries. And it has been done in the approximation cases as well. So the question is, how should we find these polytopic templates? And what we try to do is essentially get a systematic method to actually get this template. And the systematic way is essentially to create. So in the noisy network case, the creation was through looking at a deterministic model. In the data compression, we look at a appropriately chosen lossless data compression model, and that will enable us to get these insights. Okay, so we will illustrate a lot of the ideas with the following situation. This we call source broadcast. Suppose you have a source that you want to send over a noisy channel, and there are, say, many receivers. Each of the receivers wants to reconstruct the source at, say, maybe different distortion levels. Now, clearly, in general, what is known from a very long time ago, as I mentioned, source channel separation is actually not optimal in this case. So, in other words, what we have to characterize is how much does joint source channel coding, how much can it be better than separation? That's really what we are trying to characterize. So in order to do this, I will take a digression which looks like a digression, but it's really not. We'll look at what's called the multiple description problem. So the multiple description problem is the following. It has actually a fairly ready motivation from many things that you might do. Suppose you want to stream a video over, say, over the internet. So you have a server, and it's got the video, and you want to stream it, and you want to stream it over an unreliable network. Links get lost, routes get disappear, etc. So you may want to protect yourself by saying, okay, I not only establish one path, I establish multiple paths. And so what you want to do is you want to basically somehow have graceful degradation with respect to routes. So what you want to do is that if the trivial thing to do is send the same information over all routes. In which case, if you get any one, you get a certain level of guarantee. So if you get any one, but then the difficulty is that if you get two, you get no enhancement. So what you want to do is you want to get information such that you want each of what you send here to be different but individually good. That's the tension in multiple description. So the symmetric version of the problem says that if you get any one of them, you want to guarantee the, say, like the lowest distortion. If you get two of them, you want to get a better distortion. And if you get all three, you want essentially the best. So essentially, they should mutually refine each other, but be different. That's really what multiple description is about. And what is the connection between multiple description and source broadcast? So if you think about it, multiple description is really like source broadcast. Essentially, that if you look at the source broadcast, you said that you have a source and you have different receivers requiring different distortions. Multiple description is exactly like that. So one receiver, say, has access to only one of these links. So if you have 3 descriptions, you have 7 receivers, each requiring a different distortion. They may be the same in the symmetric case. It may only depend upon the number of links you have, not the subsets. But essentially, there's an immediate correspondence between the source broadcast problem and multiple description. It's essentially exactly the same. Okay, but it's just that it's a deterministic broadcast channel. It's a graph, essentially. Okay, And multiple description problem has been studied for a very long time. It's actually been was proposed in the late 70s by many people, and there have been very nice results. For example, for the Gaussian case, Elgamal and Cover came up with an achievability scheme which is actually proved to be optimal by O0. And for two descriptions, and for more than 2 descriptions, there have been several very nice achievability schemes, but there is no complete answer even for the Gaussian case. Okay, and with quadratic distortion measures. Okay. So what I want to describe is a methodology that leads to an approximation result. And this is the picture. So remember, I just said that we can essentially get an approximation result by essentially getting polytopic templates. So what we show is that you can sandwich the multiple description rate region between 2 polytopes. Polytopes, for example, in the 3 description case, which have matching parallel hyperplanes, which are separated by at most a fraction of a bit, independent of distortion, and essentially says that, okay, we don't resolve the problem completely, but we are essentially within a bit of resolution for Gaussian. And in fact, this works also for non-Gaussian, but with quadratic distortion measures. So we'll see how this methodology it works. Okay. So here is the idea. So essentially, the idea is to create the underlying lossless problem. The underlying lossless problem is the following. So think of what we call this multi-level diversity coding. In fact, historically, multi-level diversity coding was invented by Jim Roach in his PhD thesis at Stanford, and also by Raymond Young. And in fact, the first preliminary examples using multi-level diversity coding were the first examples where network coding was used. And in fact, network coding actually arose from Raymond's observation in multi-level diversity coding, actually. So this is sort of historically how they're linked. Anyway, what is multi-level diversity coding? So in the symmetric multi-level diversity coding, this problem is the following. You take streams V1, V2, V3. And what you want to do is that if a decoder gets any one, and you want to encode it into 3 descriptions, if a decoder, so the way I'm describing the decoders is the following. 100 means that it got description 1, it missed description 0 and second and 3. So that's a binary. So 010 gets the second one, 110 gets 1 and 2 and misses the third one, and so on. And 111 gets all of them. Okay? So it says that if you get any one description, you want to decode stream V1. If you get any 2 descriptions, you want to decode V1 and V2. This is lossless. So you want exact or asymptotically exact reconstruction. And if you get V1, V2, and V3, if you want to get all 3 links, you want to decode all 3. That's really multi-level diversity coding. Okay? This is the symmetric version, and of course you can think of the asymmetric, which is for any subset you can ask for. Okay? How is this connected to multiple description? You can think of saying, the multiple description says that if you get any one, you want a reconstruction which is corresponding to a certain distortion. Any 2, you want a better reconstruction. If you get 3, you get the best reconstruction. So a simple-minded way of an achievability scheme is plugging these 2 ideas together. How do you plug these 2 ideas together? You take a layered coder. You take a source, you create a hierarchical description of the code. Say like you have a video or an image. You create a successive refinement. So you have a base layer, which I described by U1, an enhancement layer, which enhances the base layer, which I described by U2, and another enhancement layer, and so on. So now you take a source, you get a successive refinement or a hierarchical description of it. Then you plug it into this lossless multi-level coder, which means that if you get the first description, you will be able to reconstruct the first stream and therefore the base description. If you get 2 of them, you're going to be able to reconstruct the base layer and the enhancement layer. Right? And if you get all 3, you can reconstruct the finest one. So this is a very simple-minded way of architecting a multiple description. Okay? So the question is this any good? In fact, you can think of this as really like concatenating unequal error protection. So essentially it says that the last layer, the third enhancement layer, essentially is useful only when all 3 descriptions are there. So there's completely no redundancy. The second one is useful when you lose one of them. So it's like a 3-2 erasure correcting code. Okay? And the first one is useful if any one of them is to be got, if any one of them is obtained. That's just a repetition code. That's all. So essentially you see that this is really like a connection between a channel code, inherently a channel coding problem, and source coding. Now you can also construct exactly the same way if you have not symmetric but asymmetric, which means that you don't care about you don't care just about how many descriptions you got, but which subset you got. Now, of course, the number of subsets is 7, so you can essentially have to explode the number of possible lossless sources. So for every subset, you essentially create an ordering for a sequence of subsets. And this essentially says that if you get the first subset, you want to decode the first stream. The next ordering subset, you will get increasingly better streams. So this is the asymmetric version of the multi-level diversity problem that I talked about. Okay, so the multi-level diversity problem actually, the symmetric version was actually solved by the 3 description, and actually it was solved by Jim Roach and Raymond Young. And for arbitrary K descriptions was solved by Raymond Young and Zhen Zhang. The asymmetric version was what we looked at, and in fact, this is exactly where the connection with essentially network coding can also be established. So in the symmetric version, we saw that it essentially took these streams, and you never coded across these streams. You just took this, did a repetition code, overlaid on it an erasure correcting code for the next one, and no coding. But you never coded across V1, V2, V3. Okay? In the asymmetric case, it turns out that actually what you will need to do is code across, and that's essentially why we call it network coding. So you need to strategically partition the sources and code across them. And that basically can be proved to be exactly optimal for the asymmetric multi-level diversity coding. And in fact, with this, the plugging in that this structure, but now you replace the multi-level, you increase the number of hierarchical layers, and then plug it into the asymmetric multi-level diversity coding problem, you actually get an approximation result. And so all the difficulty is really in proving the outer bound, proving that this architecture is actually approximately optimal. Okay? And in a sense, we don't have enough time to go through a proof of this, but I can point you to exactly how to look at this. And I have some backup things. If you're interested, I can go through the proof. But essentially, the outer bound idea really came from examining the lossless coding problem and getting the right, what I call the polytopic template. And that essentially enabled us to prove this approximate optimality result. So what I want to do is essentially connect this back to the Gaussian source broadcast problem. So essentially what we did was that for the multiple description problem, we said that it's actually a special case of this Gaussian broadcast problem, which means that the source needs to be sent across a noisy channel, but needs to be reconstructed at different distortion levels at different receivers. And what the candidate that we are trying to examine, how bad it is the separation-based scheme versus joint source channel coding. Okay? So in this particular case, this is in terms of our agenda, it's really the first thing is where you have an explicit, in the multiple description problem, we gave an explicit scheme. Successive refinement followed by this very explicit multi-level diversity coding. The multi-level diversity coding essentially looks a bit like what's called a nested message set or a degraded message set problem. So essentially the same idea is something we will use here. The source coding will also do exactly a successive refinement coder and then give a sequence of bits, messages, nested messages, which the broadcast channel wants to deliver in a nested way. So if you really think about this is exactly a nested message problem. This is like 7 messages. And this is like a deterministic broadcast channel, which is ensuring that U1 is a common message. Everybody gets it. U2, everybody after receiver 2 gets it, etc. So there's a nested message set delivery. And that's exactly what we will do with this as well. Okay. So what we will show is that with a separation-based scheme, essentially that you will essentially get a constant approximation for this result for this channel as well. In fact, what you can show is that if any joint source channel case coding scheme can achieve a certain distortion, the separation-based scheme is at worst within a constant factor of that distortion, which translates to a constant number of bits in terms of a gap. Okay? So, well, what we will do is give you a sort of a general framework of how to think about these results. So we actually will do this in a network setting where you have many sources, many destinations. Each destination might require some version of the source, and maybe even a source can be present at multiple nodes. We're going to focus on distortion measures that are difference distortion measures, and basically we want to see whether source channel separation is how good this is in this communication network. So this is an even further generalization of the source broadcast problem that we talked about. Okay, so this is so what we will do is we know that the source broadcast is not optimal. The joint source channel coding is optimal. Source channel separation is not optimal, but we said it's within a constant factor. We will see why this happens in a minute. And we will also look at generalizations of this. So if you go to arbitrary networks, the difficulty is that you do not know how to actually separate the components. So let's see where the difficulty arises. So maybe let me look at if I have. All right. So I'll come back to this in a minute. Maybe I will do the. Oops. All right. So here's where I'll start, and I'll come back to this picture. So let's go back to how the conventional point-to-point source channel separation is proved. So how is it proved? You have a source. This is a joint source channel encoder. Transmit something over the channel. A decoder, and there's a reconstruction. And this is the separation architecture, which says that you have a source encoder, you have a channel encoder, and essentially you go through the channel. You first decode what the channel encoder did, and then the source. So the traditional theorem essentially does the following. It knows that the point-to-point rate distortion function is essentially like what we did in the first part, right? It's saying that It looks at all conditional distributions such that the distortion is satisfied and minimizes the mutual information. Okay? And we know from point-to-point channel capacity that the capacity is the maximum over all input distribution of IXY. So a way a traditional source-channel separation result is proved is basically combine these two theorems and say that, of course, if R of D is less than C, then of course this chain is successful. And the converse is proved by saying that I of S hat is just by using essentially data processing inequality. Okay? So what is one observation? Here you are actually using the explicit characterization of the rate distortion function and the explicit characterization of the capacity in order to conclude this source channel separation. The difficulty we have is that when we have networks, we may have neither or only one of them. So how do we try to prove results without having explicit characterizations for the cooperatives? And that's really what we will try to explain. So let's revisit how to do source channel separation. So here is an illustration of why this difficulty occurs. Suppose you have two sources, like the source broadcast problem that we had. The way we would do this is separation result would be like, say, I take a source channel to a broadcast and do the source decoders. In the case where the channel is a degraded channel, then there's a degraded broadcast channel, etc., and that you have an explicit characterization. But if you have a general broadcast channel, you don't know the capacity of this. So you cannot use the same methodology. So the question is, can we actually answer this question about comparing this and this without actually solving the general broadcast channel problem? We essentially got away with that in the multiple description and source broadcast, because in the multiple description it was a deterministic broadcast channel which we knew how to solve, and in the source broadcast it was a Gaussian scalar, so it was a degraded broadcast channel again which we knew how to solve. Now if you take a general network, even though we do not know the answer, so we'll need to resort to this way. So let's try to revisit this. So here's the idea. Suppose a distortion D is achievable. Suppose somebody told you, okay, there is a way in this channel. Now we're just looking at point-to-point channel. We're going to prove the source channel separation result in a different way for point-to-point channels. Suppose somebody told you that there exists a code for which such that a distortion D is achievable. That means that there exists a mapping, a source channel encoder which maps the source onto the channel, and a decoder that maps the output of the channel to the reconstruction such that the distortion constraint is satisfied. And just by overall, so you know that essentially from the point, effectively applying the point-to-point rate distortion theorem for m-length sequences, that, or the converse to that, is essentially saying that the mutual information between S and S hat has to be at least m times RD. Okay? So the key idea is to induce a super channel. So just think of this as a super channel. There is a input alphabet SM and an output alphabet S hat M. And the super channel has a transition probability S hat M S given SM. Right? That's something that the infinitely clever person has told us. So this super channel essentially has a nice property that the mutual information of the super channel is at least m times RD. So now what I do is essentially that clearly that essentially says that this super channel can support, this just says that the super channel can support rate RD. Right? That's essentially what the first observation is. The second observation is that essentially what you're doing is that if a distortion D is achievable, then since the channel can support RD, what you do is that you take the source, you create a distortion, a code with rate RD, and you use the super channel in order to convey this information. So in other words, we didn't actually rely on the source or the channel capacity characterizations in order to essentially also prove that the source-channel separation is optimal. So there's an alternate way of thinking about it, which is now extendable to networks. Does that make sense? Okay, so let's do this for broadcast. Again, now suppose you have somebody claims that D1 and D2 is achievable. Then essentially it says that RD1 and R1D1 and R2D2 can be supported on this broadcast channel effectively on a super block again. Again, what you do is let these functions be whatever the infinitely clever person who has designed this give us. This induces a super interference channel. Essentially what it says is that you have a source S1, S2, destinations which are S1 hat, S2 hat. You have this super interference channel, but you have individual mutual information guarantees because you know that you can actually achieve these distortions. Somebody has told you that. So it's like an interference channel where you're given these individual mutual information guarantees. And now all you do is essentially, since I know that the individual mutual information guarantees are satisfied, I code at the correct rates and encode these sources and use this super interference channel. And that essentially enables us to prove that in this case, that source-channel separation is optimal. The critical thing that we have used in this is that the sources are independent. So all we have proved is that if you have a broadcast channel with independent sources to be reconstructed at destinations, that source-channel separation is actually optimal. It is actually not true in the case that we looked at earlier, was that the destinations were requiring the same source at different distortions. In that case, source-channel separation is not optimal. Okay? So that's the distinction. So in a sense, what we used was the sources were independent, and each source is reconstructed only at one destination. That's really what is critical. Okay? All right. Can this now, basically now we know how to do this for point-to-point, for a simple broadcast with independent sources. Can we now generalize it to networks? All right. So first one is for multiple source unicast. So here is the situation. Suppose you have any network with independent sources, and you want to reconstruct these sources at different destinations at different distortion levels. We apply exactly the same trick as we did for the broadcast case, which is the following. Suppose this distortions were actually achievable. We don't know how, but suppose it is achievable. That means that there exists this super channel, super interference channel with individual mutual information guarantees. That is guaranteed to us by the existence of that. And all you do now is essentially do exactly the same trick, which is now you basically create this super interference channel. Since you have individual mutual information guarantees, in exactly the same way as we did this for the broadcast, we are able to guarantee that you are able to deliver this. So what we have proved with this, we have glossed over a few details which you can look through if you go to our webpage and so on and read the paper. But essentially what we have said is made a very simple observation that actually gives a powerful result, which is that if you have multiple sources that are being transmitted over arbitrary noisy networks, which could have broadcast, superposition, or whatever, and the only requirement is that the sources are independent, And the destinations are interested in only one of the sources. Each destination is interested in only one of the sources. So that's why I called it source multiple unicast. Okay? Then source channel separation is exactly optimal. Okay? So to emphasize, you can also relax this if many destinations require the same source at the same distortion level. If this distortion in the levels are different, then the problem becomes different. Okay? So here you could have channels that have finite memory. You could have networks which have superposition broadcast relays, etc. And you can also have source channel bandwidth mismatch, etc. These are lots of things that bells and whistles you could put onto this. Okay. So I'll demonstrate. So just to recapture what we said. Here, what we showed was that separation is exactly optimal without actually solving the problem. What were the component problems? The component problems, of course, was a simple rate distortion for the sources, and then delivering these messages over the network, which we don't know how to do. It's a multiple unicast problem. We actually do not know what the rate region for that is. All we have shown is an architectural result, which says that I don't know how to solve this second problem, but whatever it is, I can split the problem into two, and this is exactly optimal. So this is the first demonstration of a result where we're giving an architectural result without actually solving the individual components. We'll show exactly the same for correlated sources, but with a simpler, so in a sense a dual for this. So in the independent sources problem, in the first problem, then what we call multiple unicast problem, the sources were very simple. That the sources were all independent. The network was arbitrarily complicated. In a sense, the dual, if you wish, not technical dual, but the philosophically is that you make the sources more complicated. That is, you give correlation to the sources, but you make the network simpler. So the network is simpler by what we call noisy graphs. So the network is just a graph, but every link in the graph is a discrete memoryless or memoryless channel. That's what we call. So here, for example, what you have is, say, encoder 1 has access to S0 at S1, encoder 2 has access to S2, and each of these links are DMCs. Of course, if these are essentially bit pipes, this already includes an open problem, which is the distributed data compression problem. So clearly, the distributed data compression problem is unresolved for arbitrary distortion measures. And so if you want to ask whether separation is optimal or not, one component is again unresolved in this case in general. Of course, in this case, the network in terms of sending information over the graph could also depend upon how the message structure is. That could also be unresolved, but depends on how you separate where separation occurs. Okay. So how do we actually do this? So essentially, what we do is, again, the same way. If a certain distortion tuple is achievable by any joint source channel coding scheme, we essentially create a separation scheme, sort of achieving the same performance. So here is a sort of a cartoon idea which you will try to illustrate. So suppose that S0, S1, S2 are the sources. Decoder 1 wants to reconstruct S0 at, say, distortion D0, and S1 at distortion D11. Decoder 2 wants to reconstruct S2 at distortion D2 and S1 at distortion D12. And the question is whether how you actually can do source child separation here. So what you do is the following. Suppose that a certain distortion tuple is achievable. So somehow there has to be a mapping which enables us to achieve this. Let's call that mapping Xij. For example, X11 is the mapping that takes for encoder 1 going to destination 1. So what you do is, for a channel block input, essentially you can very coarsely simulate the channel. Right? Now, what it says is that in order to essentially, this particular channel can essentially carry at most this much bits of information. Whatever source channel code you used, the amount of mutual information you can induce over this link is at most this block mutual information. And so, what you do is essentially say that, well, what you can think about is that you are effectively guaranteed this amount of mutual information over this n block lengths, and you can essentially apply a source channel code over this simulated output. That's basically what you do. So what you've done is sort of in a crude way, sort of cleaned up the channel and created this sort of source channel separation. The separation actually is a bit more complicated, because actually you might have interaction. The extracted pure source coding problem can actually be non-trivial, which is essentially indicated here. So you might have a block of messages that is sent out. So essentially you can think of creating bit pipes out of the noisy channel and using those bit pipes, but that's a crude way of thinking about it. But it's essentially an intuitive way, perhaps, to explain why this works. So essentially, the extracted source coding problem is an interactive source coding problem, which you may not have a characterization of. But all we are saying is that using this followed by a channel coding is actually exactly optimal. Okay. So essentially, this is the basic result. And in fact, this simulation technique is adapted from a very nice observation that Kronecker et al. Did in 2009, which was from a message problem, which showed that if you have a message so if you have independent messages being sent across a noisy graph, then you can separate roughly network coding and channel coding, if you wish. And of course, in our case, the problem is different. You have correlated sources, lossy, and the translation is not exact, but actually this is a nice connection to it. Okay, and so this takes me to the last one, which I skipped over in the beginning, and then I said I'll come back to, which is now you basically can think of the third generalization, which is now you have sources now, but they may be actually destinations that require different sources but at different distortion levels. So now that's different from the independent sources with the same distortion levels. And here, the successive refinement scheme essentially splits this S1, for example, into two messages, two base layer and enhancement layer, so to speak. And now you essentially do message set delivery over this. And in exactly the same way as we did. Here it takes a bit more work, and then the basic technical result actually is related to the multiple description problem we talked about. But in some ways, again, we can prove an architectural result where shows that separation is approximately optimal within 0.5 bits of additional user. And this essentially is a generalization of the multiple description of the source broadcast result. Okay? And given the amount of time, I'm happy to go through proofs, but it probably is easier if I can talk offline if anybody is interested. And this also basically resolves the question about optimality of how good this architecture is for arbitrary number of descriptions. And we show that this result essentially shows that asymmetric multi-level coding with successive refinement for arbitrary number of descriptions is actually approximately optimal as well. Okay, so that's basically, so essentially what this graph, this picture, what we did was the following. So we went down this, we showed that source channel separation is optimal when you have source unicast or with correlated sources with noisy graphs. When it is not optimal, like in source broadcast, we actually show that in this case, multiple description at source broadcast is we actually do the approximate characterization by using the characterization of the individual cooperatives. Here we do it without. Okay? And basically going back to where I was. Yeah, this is where I was. So in fact, in certain cases, you can actually get an exact source channel code when, for example, you have broadcast with correlated sources over Gaussian channels. And there, the only interesting thing I wanted to point out was hybrid coding, which is using uncoded and sort of vector quantization is actually optimal. And yesterday, I think there was a poster which generalized this to the vector case as well. All right. So, okay, I just want to summarize with end with this. They're just saying that in many ways, what we did in this whole program was essentially create simpler models for which we tried to understand exactly what was happening. In the noisy network case, it was a deterministic model. For the last hour, we've been talking about source coding, and the simpler model we worked with was the lossless model. And that enabled us to get a lot of insights. We translate that insights to the noisy network or the lossy coding problem to get an approximation result. And in some ways, many times, you can get these approximation results and architectural insights without actually solving the individual components, which is actually sometimes nice. So in some ways, what a theory has to give you is, of course, it would be really nice if a theory gives you a rate characterization or exact characterization of what can be done. But one level of what a theory can give you is an architectural result. And even if you don't necessarily solve the individual components, if you're able to demonstrate an architectural result, it's actually, the theory is useful. And that's essentially what this tries to demonstrate. And there are many, many open problems that we still need to resolve using such techniques. All right? So that's basically it.
Probably I don't need that.